In this introductory video for Unit 1, we're going to take a general examination of statistics and how statistics fits within research questions. And so the importance of statistics is that statistics allows us to separate fact from fiction. And we'll start with an example here related to a chemical compound that our bodies naturally make, and that's called creatine. And manufacturers for supplements have figured out a way to convert creatine and make it into a supplement with the idea that if people consume the supplement, they'll develop big, strong muscles. But the importance of research and statistics is that research and statistics provides us with a way to take a very objective approach in examining whether some of these claims are true. And so before we actually get into quantitative methods and statistics, it's important to examine the research process overall. And when we think about research, it's just that. It's systematic investigation using a variety of means to establish facts and to reach new conclusions that are free from subjective interpretations. And now, in part of this process, quantitative methods allows us to apply a set of numbers, formulas, techniques to bring to light some of the answers to these research questions. And the overall purpose here is to be very objective. People can disagree on many things, but the saying that numbers don't lie is true in this case. 5 plus 5 equals 10. We all have to agree to that. But if we say 5 plus 5 equals 12, then we know that that's not logical. Statistics allows us to reach a consensus agreement on a variety of different topics. And if we take a look at the overall research process here, when generating any type of research, it always begins with some sort of theory. This isn't an idea. Perhaps there's a societal problem that's been identified, and we want to start to address that problem in a very systematic and objective way. That will lead to the formulation of hypotheses. And essentially, an hypothesis it's an educated guess. And how do we guess about the potential outcome of a proposed research question? Well, we examine history. We examine previous patterns related to our problem. We start to piece together different ideas, different theories, previous findings from other observations that may not be exactly what we're going after, but close enough. We then carry out a system in which we make observations. We collect data. This is a very common term that you'll hear very often. And collecting data is all about collecting information, whether it's through surveys, whether it's in a laboratory, over the internet, so on and so forth. Data refers to the conversion of that information into numbers so that we can be as objective as possible at eventually answering our research question. And then we arrive, based upon the numbers, we arrive at what's called empirical generalizations. So when we use the term empirical, that refers to the process in which we collected information, and then we come to a conclusion and we make some sort of generalization. This is a very important part of research where people will start to deviate in their interpretations, which is perfectly fine, but nevertheless, at this point, we then set the stage for further investigations and further research. So the last question here on this slide is, where do we fit in terms of quantitative methods? We fit right here. And so the transition between moving from observations, where we collected the data, to making those generalizations are the set of formulas, techniques, graphical analyses, all that we will address in this course called quantitative methods. Another popular, maybe not so popular way to address research is defined as the quote-unquote the research trinity, and that involves design, measurement, and analysis. And so when we talk about design, this occurs as part of the problem identification stage, where we lay out a very sound plan to carry out that research. We need sound measurements. If we're going to collect data, we want to use methods that are both valid and reliable. Without those two key components, the quality of the data we collect will not allow us to get to an answer we can trust. And then the analysis will encompass both the quantitative aspect and the interpretation of those analyses. So when we talk about design, just to review the previous slide, the design is important because it establishes the quote-unquote integrity of the research. It establishes internal and external validity. And so when we talk about validity, that goes to the believability of the results of the study. Now, the believability of the results at the end of the study is going to depend upon the design stage. So we have to have a good design, a quality design, so when we get to the end, we can have trust in the numbers. The measurement stage, we determine constructs. We set up what are called operational definitions, so that we clearly define what it is we are measuring, and by paying particular attention to the reliability of the measurements. And so when we talk about the reliability of measurements, we're using tools that we can count on. And those are tools that will produce the same thing if we measure the same thing time and time again. And then finally, the analysis establishes conclusion validity, so that goes to the trust we place in the previous two steps. So we can trust that these conclusions are based upon the measurements. And this is the final stage where we get to evaluate our initial educated guess, our initial hypotheses. So in terms of quantitative methods, the other popular term that's often used is statistics. And so when we think about quantitative methods or statistics, statistics is shorthand for statistical procedures. And just as we briefly touched on the previous few slides, this refers to formulas, calculations, equations that we apply to analyze the results of research studies or other pieces of information of interest. As mentioned earlier, when we talk about empirical, this refers to obtaining information through direct observation and measurement. So if we administer a survey or questionnaire to 100 people, they fill out the questionnaire, we take it back, that's taking an empirical approach. And so in this course, how will we use statistics? We're going to use statistics to answer interesting and important questions. And now you might think, why do I have to take statistics? Because statistics allows us to objectively understand information so that we don't have multiple different interpretations related to the same question. We want to be sure that the information we're evaluating is accurate and valid, and that sets the stage for valid and accurate applications in the future. So I like to use analogies when describing the wonderful world of statistics. And we're going to start with a basic tool that we're all familiar with, and that's a hammer. But how you view the hammer depends on the context from which you are coming to. So, for example, the engineer will look at the hammer and view better ways to design the handle for comfort and grip, as in terms of ensuring that the user of the hammer will not experience injury. The metallurgist will look at the hammer and try to devise ways of making the head of the hammer much more resilient to impact by selecting different materials based upon the chemical properties of those materials. But in our case, if we're in our class, we're going to look at the hammer from the perspective of a carpenter. The carpenter may not care about the details that the engineer used, may not care about the details the metallurgist uses, but wants to use the hammer in a way that is going to be functional. Now, if we take that analogy and apply it to statistics, what we're looking at here in the middle of the slide is a standard equation that is used in statistics. Now, the mathematician will look at statistics here, will look at this equation and try to devise a proof to ensure that this equation is valid from a purely mathematical perspective. The computer engineer will look at this equation and devise a way to bury this equation inside the code of popular computer programs such as Microsoft Excel, so we don't have to worry about inputting this equation all the time. We can just select a menu item and use the equation as it has been programmed into the code that we never see with our computer programs. Now, if we look at this equation from the perspective of a physiotherapist, the physiotherapist won't necessarily care about the theory that the mathematician has devised or the code that the computer engineer has devised, but wants to make sure that the equation that was used in a research study that justified the use of this particular exercise for the patient is valid and actually works. So what we've seen so far is that statistics is a very wonderful thing that can solve a lot of our problems, but statistics can also set up for some very dangerous situations. I introduce you here to one Eric Pullman, who was a very renowned researcher, Canadian, who investigated and made some very startling discoveries related to human obesity, aging, and menopause. He did made these discoveries in many research studies while at the University of Vermont and the University of Maryland, and published over 200 research papers, and really set the stage and was establishing a lot of unknown things in this field. The problem with his research findings is that they were made up. The data were fabricated by basically retyping numbers into various Excel sheets that led to him pleading guilty in a federal court of law. Now, he wasn't guilty of lying. He was found guilty of fraud because of his applications for research grants to the National Institutes of Health to the amount of about $13 million of research funding. Now, the data resulted in 10 research papers, at least 10 research paper retractions, but it wasn't just the punishment here just wasn't paper. He was sentenced to 1 year plus 1 day in federal prison. So this is really the extreme case that we see with research fraud. Now, something I said earlier, numbers don't lie, but as we see here, people lie. 5 plus 5 still equals 10, but a person would have to erase the 10 and write in a 12. Now, there are also other cases where sometimes the research and the data analysis doesn't quite match up to the claim. So on the left-hand side here we see an advertisement from a dairy producer that suggests that drinking chocolate milk will somehow allow you to dunk a basketball. And the selling feature here is that one serving of chocolate milk, and one serving is defined by Health Canada to be an ideal serving of nutrients. The problem based upon this advertisement is that this is false. And we're going to look at some research here in the next few videos to demonstrate how this claim is false. Now, there was another research study that linked the measles, mumps, and rubella vaccine that we often receive as very young children and autism, in that the vaccine is a cause of autism in children. And this research study generated a great deal of concern at the public level. The problem is that this claim was false. And this paper that made this original claim based upon the data was eventually retracted because it was found that the data were fabricated as well in this study. That did not link, well, the study attempted to link, directly linked the vaccine and autism development in children. However, the numbers were actually made up in that research paper, and it caused a great deal of controversy in the public realm. So this ends our first video here for the introduction to Unit 1.